Hey all, welcome back to another round of physics. And yeah, we're gonna keep moving here. So the last couple lectures, we've talked about the law of Biot-Savart, this empirical formula that relates a current to the magnetic field produced. In other words, Biot-Savart tells us that moving charges, produce magnetic fields. Now we're going to start going into the flip side of that. Okay? What sometimes is referred to as magnetic induction, or if you prefer, sometimes you'll see this called Faraday's law. And you can kind of get an idea about where this would come from. The law of Biot-Savart says that currents produce magnetic fields. And Faraday's law says, well, if currents can produce magnetic fields, perhaps magnetic fields can produce currents. Okay? So that's the byline there. Okay? So what you notice in the demonstration, what we have is simply an ammeter. Okay? That's that big digital face in the background, and it's connected to a solenoid, or if you prefer, a coil of wire. Okay. And then it runs back to the ammeter. And what has happened is that I'm taking a magnet, and I don't know which side is north-south, but we'll keep it like that. You notice, though, that the way that you actually get the needle to deflect is not when the magnet's just sitting here, but rather when the magnet's moving, either towards the loop or away from the loop. Faraday's law found that, yes, magnetic fields produce currents, but what it is it's not the magnetic field, it is a changing magnetic field. And he actually went a little bit further than that. He said a changing, so ddt, so there's a time change there, and he said it's actually the magnetic flux. And Faraday posed it as what he called an electromotive force. So sometimes you'll see this written as EMF. Now keep in mind, we're talking about, I don't know, the 1850s, 1800s, mid-1800s. And so during this time of examination, what is an electric field? What is an electric potential? Right? These terms didn't exist, or they were being developed at that time. Okay? We're kind of standardizing the terminology of the field. And so at the time, Faraday didn't recognize the electromotive force as being a difference of potential, electric potential. So historically speaking, he called it an EMF, and that has held over. But in today's parlance, if you prefer, you could think of this as a change in potential, a delta V. Now, Faraday also noticed there's a very important piece here. I'm going to put in a negative sign. Okay? And this negative sign has its own consequences, which we'll have to discuss. But sometimes you will hear that negative sign as being Lenz's law. I think it's Lenz's law. Okay? And we can look at it this way. Okay? If, let's say, the flux is increasing, okay, the negative sign ensures that current runs in the loop to decrease the flux. Okay. So if the magnetic field, the flux of the magnetic field is increasing, then current runs in the loop to decrease the flux. Okay. Or if the flux through the loop decreases, then current runs to increase the flux. And that's how we get the direction of the current produced in the wire. So we've taken care of the flux piece. We've discussed what the negative sign does. Now on the other hand, the other side, I've already said you could write this as EMF. You could write it as delta V. A different way to write it, if you prefer, using the relationship between a change in potential and the electric field, you could also write this as the change, the electric field around a loop. Let's say for a moment that I have a loop of wire. And I will go ahead and let's run a magnetic field going upwards, for example, B. Okay. Now, one of the things is when we look at the flux, you notice that we have an N hat. N hat. Now, generally, I've said that N hat has to be perpendicular to the surface. And in the context of Gauss's law for the electric field, we said that it had to be outward. Outward. In other words, away from the interior of the volume. But here we only have a 2D surface. So there is no inward and outward. Okay? So we don't have to worry about this outward restriction anymore. Okay? What I will say, however, is that once you choose a direction for N hat, okay, then stick with it. If you choose a direction for N hat, this negative sign will tell you which way the current runs with respect to that N hat. Let's go through an example here. So I'm going to say for a moment, let's say that N hat is upwards as well, parallel to the magnetic field. Okay. And while we're at it, let's say that the magnetic field is increasing. So we'll say that B is increasing. What does that tell me about the flux, the change in flux of the magnetic field? If the magnetic field itself, the magnitude, is increasing, what can you tell me about the flux, the change in flux of the magnetic field? It's also increasing. It also increases. So what you can think about is, okay, the flux of the magnetic field is increasing in time. Okay. Now here's the next piece. Okay. We want to figure out what's the direction that the current runs in the loop. So direction of I. So let's think, if the magnetic field flux is increasing, then current will run in the loop, and the magnetic field due to the induced current should be pointing down. Okay. Remember, I said nature abhors a change in flux. Nature, because of this negative feedback loop, current will run in the circuit, the loop, in order to decrease the flux, the increasing flux. It will try to oppose whatever's occurring. So if the flux is increasing, current will run to decrease that flux. That means that the current will run such that a induced magnetic field is pointing downwards, opposing the change. And I'll just call this induced. Well, if the induced magnetic field is pointing downwards inside the loop, remember we're talking inside the loop here, that means that when I apply my right hand rule, okay, so think about grabbing the wire, and the question is, if I grab the front edge of this wire, do I grab it with my thumb going to the right? Well, that would mean that the magnetic field inside the loop is going up. That's not right. The induced magnetic field should be pointing down. So if I'm grabbing the front end of that wire, okay, I should grab it so that my fingers are curling downwards when I'm inside the loop. Well, that requires the current to be running this way on the front side of the wire, so that when I grab it, I'll draw it in real fast, grab it with my thumb going in the direction of the induced current inside the loop, the induced field is going down. Similarly on the back side, and you can check this, but of course once you have the direction for one piece, you have the direction for the entire wire. So in this example, in this situation, if the magnetic field strength is increasing, the flux is increasing, the induced magnetic field will want to oppose that increase, which means inside the loop, it should be pointing downwards. And that means that current should be running in the direction shown in the figure. Well, if current is running in that direction, what direction is the electric field, the induced electric field? Call it induced here. It's the same direction. It must be going in the same direction. So I'll do that in purple. My induced electric field must be going in the same direction as that induced current. Okay. Cool. Good. Good. And incidentally, I'll say, now that we have taken into account, when we do this direction of the current, we're taking into account that negative sign. And we've taken that into account. Go ahead. See if you can produce the argument. Think about if you have a loop of wire and you have a magnetic field. We'll say this time we'll call it, let's make life interesting. Let's call it the external magnetic field is pointing down and the magnitude of that magnetic field is decreasing. Go ahead. What's the direction of the current flowing through the loop? And what's the direction of the electric field? You got it? Good. Well, if the external magnetic field is decreasing, that means that the flux of that magnetic field also decreases. I don't know why I'm spelling this. I should just use arrows. Okay. So if the flux is decreasing, that means that the induced magnetic field, it wants to be pointing in a direction to oppose the decrease. So you can think of this arrow getting shorter and shorter and shorter, right? That represents the decreasing magnetic field. So the induced magnetic field wants to prevent that arrow from getting shorter. So it must be pointing downwards. B induced should point downwards to try to prevent that decrease. Well, if the magnetic field is pointing downwards, the induced magnetic field is pointing downwards inside the loop, that means that when I grab the wire, I have to make sure that my fingers curl down when I'm inside the loop. So again, if I'm grabbing the front face of the loop, okay, I have to grab it with my thumb going to the left, my left, so that as I curl my fingers down inside the loop, I have the field pointing downwards. So again, it actually turns out in this situation the current should be flowing, I guess this would be clockwise when viewed from above. And again, that ensures that the induced magnetic field is pointing down when we're inside the loop. Okay. So I do not encourage you to memorize these. Okay, don't memorize these. Think through the process. Okay? And the reason I don't encourage you to memorize these is because you see that a situation with the magnetic field pointing up and increasing is the exact same, will result in the same current as a magnetic field pointing down and decreasing. Okay? So you can get similar outcomes with different arrangements of the external magnetic field. So I do not encourage you to actually memorize the situations. Rather, walk through them, right? Think about, what is the external field doing? What does that mean about the flux? Well, then which way does the induced magnetic field have to be? And then use the right-hand rule to get the direction of the current. Okay? That's what I would encourage you to think about, okay, walking through. Okay, I think I'll stop there for right now, but keep chewing this stuff over. Thanks for your attention. I'll see you next time.